morning, Mr. Tarrou. Okay, we have learned so far this year how to handle a single piece of data. Like, let's say, what's the probability that I find somebody that's over 5'10"? And that population of whatever we're talking about, adult males, is normally distributed. Just do a z-score calculation. Then we learned about discrete random variables. In those settings, you can count the number of outcomes. And there's formulas for a discrete random variable, mean and standard deviation, but we don't use those formulas unless we have a PDF table where all the specific outcomes and all those probabilities are given. Then we just learned about the binomial setting, which is when we have two possibilities, there's a set number of observations, there's independence and a constant probability of success, and we can deal with binomial settings when they're recorded as a number of successes from a set number of trials, or a percent of successes out of a set number of trials. That was the binomial setting, binomial count, and what we just studied, which was binomial proportions. Woo! Okay. Well, now we're going to deal. Oh, we also had the geometric setting where you went to your first success, and everything else sounded the same as the binomial setting. Well, now we're going to work with sample means. And if you're analyzing multiple observations, and each one has more than just two outcomes, like pass, fail, or yes, no, then you may be setting up a sample mean variable, like GPA, blood pressure, shoe size, and etc. Let me pick on the shoe size idea here. When you measure somebody's shoe size, most shoe sizes are in half sizes. 6, 6.5, 7, 7.5, 8, and so on. So I can actually state or count those outcomes. There is a minimum shoe size and a maximum shoe size. You know, you could have like your really huge sizes, like from the world's tallest man, or basketball players where it's, you know, shoe sizes of 17, 20, 25. You know, I don't know how big those record-breaking sizes are, but it is a countable variable. So let's stick on that idea. We randomly select 30 male adults, and we measure the size of their foot, or hence their shoe size. That's a discrete random variable, the individual measurements. But if I then say, well, if I take 30 men, I measure the length of their feet or measure their shoe size, and therefore make it say, well, what is the probability that if I take a sample size of 30 men, their average shoe size, not individual shoe sizes, but average shoe sizes are above a 10? Well, when you take that discrete random variable of shoe size, you take, I forgot what I said now already, 30 something, whatever amount you collect, you add all those up and you divide, you're of course going to get a decimal. And the larger the sample is, the more your decimal is probably going to run on. And thus, we go from a variable that is individually a discrete random variable to an average of a collection, maybe the average of 30 measurements. That becomes, therefore, a continuous random variable. So if I said, well, what is the probability that a randomly selected adult male has a shoe size of over 10? Well, if I have a PDF table of all the sizes and all the individual probabilities, maybe I would just add up all the probabilities for 10, 10.5, 11, and so on until I get to the end of the PDF table. Whereas if I said, well, if I take the collection of 30 men, what's the probability that the average of all 30 men's shoe sizes is over 10? Well, then that's going to be a calculation, a z-score calculation, or possibly a t-score calculation. You'll not hear this in today's lecture, but when you're working with means, there was going to be some times where you do a z-score, which is all my students know at this point, and then occasionally you'll be doing something called a t-score. That's a concept that's going to be coming up in my class very, very soon. That's when you're working with averages and you don't know basically anything about the population. All you have is the data that you collected from your sample. So you'll have a sample standard deviation as opposed to a population standard deviation. And we'll get into that more later, but for now, let's just stick with z-scores. Some characteristics of sample means. Means of random samples are less variable than individual observations. Take the shoe sizes. Some people have really, really tiny feet, some people have huge feet. Take the money market, not money market, but like the stock exchanges. You see, if you turn the stock markets on every day, you'll see those values gyrate wildly. But if you then choose, well, let's show me the 30-day moving average, where it shows you the average of the previous 30 days of values, then you get this nice smooth curve that's easier to see what the trend is, instead of all this jagged up and down movement. So averages will sort of like shave off or wear down the max and the min values and give you a smoother, less variable statistic. You're going to learn a lot about something called the central limit theorem. That explains how the distribution of means are more normal than individual observations. I'll get to more than this later, but the central limit theorem is a hugely important concept. Do more than just watch this video. Read your book and take notes on that central limit theorem. It's what allows so many settings in an Intro to Statistics course to be done with a normal approximation or a t or z score, because the central limit theorem will allow you to pull numbers out of a distribution that's clearly not normal, but yet the distribution of averages will be. I'll get to more of that at the end of this video. All right, page 2. Woo! Okay, in the binomial setting, we had 4 checks. 2 outcomes, set number of observations, independence, and constant probability. Well, if you're going to decide, or you've figured out, or you've concluded that you're working with a sample mean, or you're working with means, not proportions, then there's 3 checks. Random selection from an SRS. No matter what kind of test we're doing or what type of variable we think we're dealing with in Intro to Statistics, all of the data must have come from an SRS. Independent observations. It's often, but not always appropriate, but it is very often just simply check that yes, an SRS was taken and the population is over 10 times the sample size. This must be true to use any of the standard deviation formulas. I'm talking about the population being over 10 times the sample size. Now, there will be some settings in these applications that just simply saying it was an SRS and the population size is over 10 times the sample size, where it's just not appropriate. If you are an archaeologist and you found some fossils, you can't just do an SRS of the population. You can only work with what you have there in the ground. Well, if there's any possibility that this large collection of fossils being sort of like a family unit, maybe you're studying some kind of animal or prehistoric humans that were nomadic in nature, we'll have to maybe draw conclusions off of those fossils that we find, draw a conclusion about the entire population, but the whole idea of an SRS, and especially the independence, might be put into question, because maybe there's some sort of family genes that are shared between those fossils that have been found. But this is really common and usually appropriate. You can just simply say the normality is stated, or once again bring up this idea of central limit theorem, which we'll talk about in the last page. With a large sample of n, the sampling distribution of the means, okay, we're not talking about raw data, but the means, will have approximately normal distribution of n, and this is, you remember your shorthand notation for normal distributions, capital N, and then mean and standard deviation. That's how you describe a normal distribution, the mean and standard deviation. Or the mean of a sample mean is the same as the population mean. That is true for any statistic or variable that is unbiased. Law of large numbers says that this happens. And the mean of your sample's mean, or the standard deviation of your sample's mean, is equal to the population standard deviation divided by square root of n. Now, in Intro to Statistics, a lot of times we do use z-scores and thus call things sigma, or standard deviation of the population. But a lot of times in the real world, especially when you're not in a textbook, we do use means a lot. A lot of settings are not binomial. A lot of measurements that we take do not have just 2 outcomes. So when you're working with these sample means, a lot of times we just have the information that we collected from our sample. And if that's the case, when you're working with means and you only have the sample standard deviation, which is not what I have written here, I'm just giving you a preview of what's coming up, then you'd be doing something called a t-score instead of a z-score. And if you have the sample standard deviation and that was it, then this formula would be called standard error of the mean. Just giving you a preview again of what's coming up. At this point in my textbook, we're still being given the population standard deviation, even though in the real world that's not usually known. Just to kind of simplify and ease you guys into these statistical analysis tests. All right, last page, and we'll finally give you not a demonstration, but an explanation of what central limit theorem really is trying to discuss or show you. Bam! Okay, so we talked about sample sizes and what's appropriate for the central limit theorem to ensure the averages are normal. Here's kind of a guideline. Required size samples of n for the central limit theorem to ensure normality for the distribution of the averages is the sample size of less than 15 is going to be okay if your distribution of your raw data or your population is close to normal. If there's some skewness to the raw data, if there's some skewness to your sample, or if you know there's some skewness to your population, then you want a sample size of between 15 and 30. And if you know that your population standard deviation is skewed, or you see a strong skewness with just the sample distribution, not the distribution of means, but the samples distribution, then you need a sample size of 30 to make sure the central limit theorem will say or create this normal distribution for you for the averages. Now let me give you at least an example or a discussion of what I'm talking about here. Now we know that questions involving money, I'm sure you can find an example, but pretty much questions that always involve money are going to be right skewed. You know, there's a lot of like low-end workers and then just a few CEOs in the company, or a lot of people on the team, but there's those 2 or 3 like star players that get all the press and all the money and all the endorsements. So money questions will pretty much always be right skewed. So if we have a right skewed distribution about money, and then somewhere there's some kind of population mean, you know, I could not say, well, what if you pulled one person out of the population and you asked them, you know, how much do you make? What would be the probability that they would say over $25,000? Or any value, for that matter. You would not be able to answer that question because you're pulling that one person out of a right skew distribution, and we don't have any techniques for dealing with probabilities of a skewed distribution, at least not if we're going to do some kind of normal approximation. Maybe if you have a geometric PDF or a binomial PDF distribution table, you can just pull numbers out of that, and maybe it would look right skewed if you were to graph it. But to do Z or T-score calculations to approximate these normal probabilities, that's not possible. So maybe you took, instead of just one person out of the population, you took maybe 5 people out of the population. So you took a sample size of 5, and you took those 5 incomes that people stated they made, and you averaged them together. Well, that, you know, if you were to take another 5, and another 5, and another 5, and another 5, and you get the idea, and take all those averages and display a distribution of the average of 5 people's respondents, not just one by one, then that distribution of averages might look something like this. I'm trying to show a little bit of right skewness here still. If your sample is unbiased, the mean of your sample is supposed to be the same as the mean of the population. But you might still have, with a sample size of only 5, you might still have some right skewness, but the shape is starting to change. Not the shape of the raw data, it's still going to be very right skewed, but the shape of the distribution of the average of 5 people's incomes will start to appear to be a little bit more normal. I'm not loving my graph there, but it's less skewed. Then, if you come in, and let's just do 2 pictures because I'm not really loving my skill of drawing there, and say that I took a sample of 40 people. So I averaged 40 scores, 40 income values together, and I made a distribution of that. So that's, again, asking 40 people how much they made, take an average of those, you know, add all those up and divide by 40, find an average. And then that would what you would do in real world, but as far as talking about distributions, you know, maybe you do another sampling of 40 and you find another average, and another sample of 40 and you find another average, and you take another sample of 40 and so on until you have many, 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 many samples of that, and you can make a distribution of those average values. That distribution is going to be very, very normal. That's what the central limit theorem says. So that would allow us to answer a question of, well, if I ask 40 people what their incomes are, what's the probability that the average of those 40 individuals incomes are greater than, say, $25,000 or $30,000, or less than $10,000, or more than $100,000. The point is, I couldn't ask you the probability that one person makes over X number of dollars because it's a right skew distribution. But I could, because the distribution of averages are going to be normal due to the central limit theorem, say, well, if I sample 40 people, what's the probability that their average of those 40 people's incomes are over a certain number of dollars? That could be done. That's the power of the central limit theorem. That's why normality is so important and why we talk about it so much in this book, because when you're working with averages, the central limit theorem will ensure that distribution of those averaged values is going to be approximately normal, even if the raw data is skewed, and it just allows us to work with a lot more settings than otherwise we would be able to. It's also, again, what turned that original example of shoe size, which was a discrete random variable, and allow us to work with it as a continuous random variable, because it's the average of a lot of discrete values, and thus you get decimals, and that turns into sort of a continuous random variable. So I'm Mr. True. That's the best I can do to describe the sampling means idea and central limit theorem. Let's do some examples. Woo! Bam! Go do your homework, or please watch my next video.